Hi, this is Pick Computer Science video number 3, where we look at the little man computer and see how it can help to model the behavior of CPU registers. To do this, we're going to be using the Durham University implementation of the little man computer, and we'll be keeping an eye on those 5 CPU registers that are symbolized in red there: the accumulator, the program counter, the current instruction register, the memory address register, and the memory data register. So here is the instruction set for the Durham LMC, and we're going to be using some of the instructions in here to write the simplest of little man computer programs, which is just going to allow a user to input a number and the LMC will just output that number again. So the commands we're going to need are those ones there: in, out, and HLT. In's machine code equivalent is 901, the equivalent of out is 902, and to halt, HLT, the machine code equivalent is 000. So just a little recap about which register is symbolized where exactly on the screen. The calculator here we would equate to the accumulator. The counter here, the program counter. There's the MAR and there's the MDR. And we might say that the CIR, the current instruction register, is the data we would see just inside the little man computer box here. I'm going to refer to this whole box that does include the MAR and the MDR as well as maybe the engine of the CPU, the mechanism, the workings, the thing that makes things happen. The program we're going to write is very simple. I could load it up from a file, an external file, but I'm just going to type it in to the first 3 boxes there: 901, 902, 000. The idea is I'm going to step through an animation of this program to see how our different registers behave. So notice first of all, within the engine, in the CIR we've got dash dash dash, and likewise in the MAR and the MDR. That's because the program hasn't started yet. We'll see those values change, and we'll see values in the accumulator and the program counter change as we go on. So my first job is to click on one step, which will just do one part of this program. So I click on it, and what happens is the engine goes and visits the program counter, and it sees that the program counter is currently at 0. The console is backing that up, and it sets my MAR, memory address register, to 0. And what this means is that the first memory address, the first mailbox that we're going to go and check and read from, is going to be mailbox 00. Also note that the CIR inside the engine is now set to fetch. So this was the first step in a fetch execute cycle, part of our von Neumann architecture. So I'm going to click on one step again and see what happens next. And what happens next is that our engine has incremented our program counter, and the console's telling us that as well. It's setting it to 1. It's interesting that it increments the program counter. The engine increments the program counter while still holding the previous value from the program counter. So it increments the program counter before it uses the value in the memory address register. Note that our status in the CIR is still fetch. Another step sends the engine up to the mailbox that it needs to check, mailbox 00, and it reads the data that's in mailbox 00, which is 901. That's our command that we want to use first of all. And that goes now into the memory data register here, and we're still on the fetch part of the cycle. Another step, and our MAR changes. It changes to 01. Now the reason behind this is that the last 2 digits of the command are 01. So it stores that in the memory address register. Now coincidentally, that's going to be the next mailbox that we check anyway, but it's happened to put 01 in there, not because 01 is the next mailbox we're going to check, but because that is the operand part of our machine code here. It's just coincidental it happens to be the same number that we're going to check next. Notice that the CIR now states in, which means we're actually going to go and get some input from our user. So we do one step again, and the engine zooms over to the input part of the screen and is now expecting the user to input a number. So if I put in a value and click on OK, now the engine zooms up to the accumulator, the calculator, and pops the value from its MDR, which was updated when we did the input. So you'll notice that the MDR has changed to the value that was input, and that is then copied into the accumulator. Note at this point that the CIR is telling us that it is done. So one cycle of the fetch execute cycle has been completed. So one more step and our engine heads back over to the program counter. The MAR did flash red there, and that's because it has retrieved the new value from the program counter. It just coincidentally happened to be 01 already, but it has refreshed with the same value 01 from the program counter. We're back in fetch mode again now, so another step should increment the program counter again, and now the engine heads up to memory address number 01, where it retrieves the command 902 and pops that into the memory data register. We're still in fetch mode. Another step pops the value 902, pops the value 02 from the operand part of the command into the MAR. And this time, because it's an output that needs to be achieved with the command 902, and notice that the little man CIR did say in, interestingly, we head over to the accumulator, get the value 041, then to our output area of the screen to output that value. Another step takes us back over to the program counter. We retrieve 02 and pop that into the MAR. Again, it coincidentally already was at 2. Another step, we increment the program counter. Another step, we go and read the address from the value from address 02, which this time is 000. We haven't come across this one yet. We'll see what it does. One more step. It pops in the operand into the MAR. Another step, and our console tells us that the program is halting. So all programs that you build with the little man computer should always have a 000 in the mailbox where you want the program to stop. So hopefully, having seen, albeit in an extremely basic program, how those registers are updated and how those registers interact with that program we built in the little man computer, hopefully that's going to be useful in getting your head around some definitions of those registers, such as the program counter stores the address of the next instruction, controls the order in which instructions are retrieved and executed, and as we saw, is incremented after being read. The MAR stores the address in memory of the location of either the next instruction to be used or the address of the next piece of data to be read. The MDR. The contents of the address specified in the MAR are copied to the MDR. So we saw that with some of the machine code and the operand part of the machine code, the last 2 digits was always copied into the MAR. So that will either be an instruction, data to be used within an instruction, or data to be copied to an address. There was the CIR. This holds an instruction whilst it is being decoded or executed. If contents of the MDR are an instruction, this is copied to the CIR. The instruction is made up of an opcode, short for operation code, the first part of the instruction. So the 9 part, for instance, of 901 is the opcode, and the address of data to be used with the instruction. That's the last part of the instruction, the last 2 digits, the operand. And then of course we saw the accumulator, or calculator as it was termed in the LMC. This holds the data being processed, holds the results of processing by the ALU. All input output goes through the accumulator. You saw that something was inputted by the user, it went straight into the accumulator. We had to go to the accumulator to get a value before it could be outputted. In our next video, we'll look at how we can use the LMC to do something really useful. Bye for now.